coming back to our slides, I wanted just to touch on one note of propensity scores matching, which is a super popular method, and you might have seen it or heard about it in other settings. But there's a lot of math-related reasons why it might not be great to use propensity score for matching if you're thinking about identification purposes. So again, in this idea of unconfoundedness, we're using matching on propensity scores to actually identify a causal effect, right? So there's some researchers that actually argue that propensity scores are okay, especially if you use them like for weighting and things like that, but not necessarily for matching. And one of the biggest proponents of this is Gary King. He's at Harvard. He's a great researcher and does a lot of work on matching. He's actually an advocate for coarsen exact matching, which is one of the methods that I talked very briefly at the beginning, where basically you take your covariates and coarsen them and in like chunks, like quintiles and things like that, and then match exactly on those coarsened values of your covariates. Again, that gives you a great balance a lot of the time. Might reduce your sample size though, so there's a trade-off between being closely matched and again efficiency in terms of sample size. But it's something that you should think about, basically because propensity score matching relies also a lot on the functional form of your propensity score model. Okay, so basically what variables you include or not include and what functional form you use to estimate that propensity score. So those are things that you should have in mind, because a lot of the times it can actually, as Gary King shows in certain examples, it can actually exacerbate imbalances. So it's always a good idea that if you're using a propensity score as a matching, for matching in this case, you always check balance, make sure that it is done correctly. And again, because propensity score matching works on expectation, you should also think that maybe with your sample at hand, it just doesn't work very well in terms of balancing. So those are things that you should always keep in mind in that case. And again, using different methods for matching in that sense could also be a good idea to see whether your results are robust to your choice of matching strategy or not. Okay, so in that case, for instance, you can run coarsen exact matching using the match-aid package as well. So go ahead, do that, play a little bit with the data, and see how your results change, or if they don't change at all. So finally, in the last part here, what I wanted to talk a little bit about is weighting, which is basically a close cousin of matching, okay? You can think about it sort of in the same way, but now we're not keeping the units of analysis intact. We're basically going to be giving different weights to observations so that two samples will look alike. And any two samples, you can think this actually outside the idea of causal inference, and it's used a lot, for instance, in surveys and things like that, to make samples representative. One of the most popular ways to use weighting is actually inverse probability weighting, which basically what it does is make some observations more important than others, depending on the probability they have to be on a specific group. So for instance, in the sense of causal inference, if you have a treatment and a control group and you want both of them to look alike, you can actually make the treatment and the control group look more like each other by using average treatment effect weights, okay? And these weights will be built in the following way. It's the treatment assignment over the propensity score for one unit, plus the 1 minus the treatment assignment over 1 minus the propensity score. So basically this means that for units in the control group, their weight will be 1 over 1 minus the propensity score. Remember that the propensity score is the probability of being in the control group. So basically this is 1 over the probability of being in the control group. While the observations in the treatment group will have weights that are 1 over the propensity score, which is 1 over the probability of being in the treatment group. So what happens with observations that are very likely to be in the treatment group? So if an observation is very likely to be in the treatment group because of their characteristics, then their propensity score is going to be very high, okay? Almost close almost close to 1, right? So this weight, in this case, it's going to be very close to 1. If they're very unlikely to be in the treatment group because of their characteristics, but they're still in the treatment group, then the propensity is going to be very low. It's going to be a very small number. Imagine like almost getting down to 0. So because we're dividing and this is an inverse probability weighting, this means that this weight for that unit is going to be very big. It's going to be huge, okay? So what we're doing here is putting more weight on those weird observations that maybe shouldn't be in that group and are in that group, versus those observations that that are very likely that we find in either the treatment or the control group. And the same thing happens with the control group. Observations that are very likely to be in the control group will receive smaller weights than observations that are kind of weird in the control group and that you would expect just by the propensity score to be in the treatment group, but for some reason they're in the control group. So those observations will receive a huge weight, and again, the less weird observations will receive smaller weights. You can do the same thing if you want to obtain an actual average treatment effect on the treated, okay? So in this case, you would multiply the same weights that we had before by the propensity score. So in this case, observations in the treatment group will all have constant weights of 1, because remember, we're trying to make the control group more similar to the treatment group. So the treatment group doesn't need to change at all. They already look like the treatment group. They're the treatment group, right? While the control group doesn't look like the treatment group. So in order to make them look more similar, we basically give them a weight of the probability of being on the treatment group over the probability of being in the control group. So basically it's like an odds in that sense of being on the treatment group over the control. So why do observations in the treatment group get a weight of 1? I already mentioned this because basically they already look like the treatment group, so we don't need to actually do anything about it, right? I'll let you think about what happens if we want to get the average treatment effect on the control group. So basically meaning that we want to make the treatment group look more similar to the control group. How would you change this weight equation? Just think about that. Another thing that's important, so in the previous slides, we looked at the fact that we want to make the treatment group look more like the control group, or the control group look more like the treatment group, or just make the two groups look more similar to each other. Another important way that you can use weighting is actually to approximate to a population. So now imagine that you have a randomized controlled trial sample that was a convenient sample, so it's really not that similar to a larger population that you want to make inference on. You can also use weights in order to make that experimental sample look more like a population sample that you're interested in. So there's some assumptions there, of course, when you go from a sample average treatment effect to a population average treatment effect. And some of the things that you need to have in mind is, in this case, that we are assuming that our experimental sample was selected on observables, okay? So basically all I need to do is adjust their observable characteristics in order to get the effect for the population. A lot of the times, of course, that is not the case. There's a lot of unobservable characteristics that that play a role about being selected into an experimental sample. For instance, just the willingness to consent to participate. That's a huge one. But if we assume that people are just random at that and at participating in that sense, then if we adjust their characteristics to make them more similar to a population of interest, then we might be able to get a population average treatment effect and not just a sample average treatment effect. So basically we can do the same thing and use the formula for the average treatment effect on the treated. But now that propensity score will not be the probability of being assigned to treatment, but the probability of being in the population sample, okay? So again, imagine that you have a big sample. Some of those units are your experimental sample. Other of your units are just population in general, okay? and they might have not even participated on the intervention. It doesn't matter, we just need their covariance. So in that case, your propensity score will be the probability of being a population observation. So again, you would put 1 for those population observations and 0, for instance, for that experimental sample. And you would do the same thing with the weights for the average treatment effect on the treated. Give a 1 weight for that population sample and another weight for the experimental sample. So in this case, it would be like this. It would be the probability of being in the population sample over the probability of being in the experimental sample. And you would do exactly the same, and basically that way you'll be weighting the characteristics of the population on your experimental sample. And you would make your experimental sample look more like a broader population. So now let's go to R and work a little bit with the weighting strategy. Okay, so now we're here in R. We saw already that we did the different matching strategies. So we want to build weights. So we're gonna build first. We're gonna do inverse probability weighting. So we need to estimate first a propensity score. Okay. So let me just write the model for the propensity score. So remember that in this case, it will be the treatment on all those variables that we already had here. So I'm just gonna copy and paste this. Great. The data that we have is the sample. Again, we're gonna just use the smaller sample, but you can use actually the big one. That's totally fine. The family is binomial, and the link is a logit. Okay, and I'm just gonna run this model. Great. Okay, so basically now I need to incorporate that propensity score into my data frame because I'm gonna use it to build the weights. So basically what I do is augment this sample, and this is from the Broom package. Okay, there's one augment in the generics package that we've also used, but the one in the Broom package works really well for this case as well. So basically what we're gonna do is see augment, and as you can see, you can also go, if you don't know the arguments, I sometimes forget. So as you can see, this is the one in the Broom package, so we're gonna go here. And basically, you can see the different ways that you can do this. We're doing a GLM in this case, so let's go here. Great. And it basically tells you all the arguments that it needs. So in this case, the first argument that it needs is the model that we already fitted, so that's great. The second one is the data, basically, if you're not the data that we need, which is the sample, because we're going to augment that data frame. We don't need new data in this case, so that's fine. Type predict is an important one because remember that by default it gives you the logit, okay, the log odds, which is ridiculous. We don't need that. We want it to be the probability, so we put right there response. Okay, so let's just see this. Hopefully it works fine. Great. So we can see here that we have the same the same data frame as before. Okay, you can't see all the variables here, I'm sorry. But if you see here, you can see that we also have the fitted values, which are the probabilities. We have the residual, the standardized residuals, the predicted, the y-hats, and things like that. Okay, so great. Awesome. So now we go to, we need to build our weight. So what we do is basically use mutate. I'm gonna build both the weights for the average treatment effect and the effects and the weights for the average treatment on the treatment. Okay, so if you remember, the weights for the average treatment effect was the treatment assignment over the propensity score, which was fitted in this case, and 1 minus the treatment assignment over 1 minus the propensity score. And I'm also going to generate the weight for the ATT, which in this case was just content. You can also do the full thing, but it doesn't really matter. It was the propensity score times the treatment assignment over the propensity score. Plus, again, the propensity score times 1 minus contact over 1 minus fitted. Okay, I think that's good. So we run that, that's great. And we can go here, and as you can see, we got our weights for the average treatment effect and our weights for the average treatment on the treated. Okay, awesome. How do we use this though now? So first thing that we want to do maybe is probably check balance first. Okay, so we want to see whether our weights are working or not. So for this, we're gonna use the package Cobalt, which is actually really useful in terms of balance. And we're gonna do the BALTAB, okay? Here on BALTAB, what we give it is basically a vector of the covariates. So very similar to mean tab in that sense. A vector of the covariates and a vector of a matrix of the covariates and a vector of the treatment assignment, things like that. But first, we need our matrix of covariates. So let me do that first. Sorry. So we do this the same way we've done this before. I'm gonna generate a matrix of covariates, and by that I just simply select the covariates. So again, I use the select function from dplyr, and then just use the covariates. Let me just use the covariates here. So again, no. I don't include the strata, you can include it. It's good. Okay. So that would be my vector of covariates. Then let's just see what are the things that we need in this case. Okay. So we're gonna give him a data frame and weights. So what we do basically is do the BALTAB, give it the covariates first, which is the sample covs, right? Then usually what we need to give it is just the vector, but let me just check. Yes. So then we just need to give it the treatment assignment, which in this case is contact, right? The data we don't care, and weights, we're gonna give it the weights for the average treatment effect. Okay, and let's see how this works. So it takes them in a second. This just means that it assumes a pooled standard deviation for both groups. And basically these are the variables that we had, right? So basically we had persons, which is a binary variable. The difference is less than a little bit over 1% standard deviations. The same thing with voted in 2000, voted in 98 also. All of these have very small differences. Not perfect, but very small, okay? So there's a 2.5% imbalance in age, but overall, it's pretty good. Okay, great. Let me just check something, because I think that here you can also include factor variables, which would be great in this sense. So I'm going to include the strata there to see if this works fine. Let's see. This is a good way then to create balance tables without having to transform your factor variables into numeric variables, which is great. No, so no, it actually considers this as a continuum, so you would have to include it as a factor in that sense. Okay, so no luck there. Okay, so we checked the balance. We saw that it was pretty okay in terms of the difference in characteristics. Again, strata is a bit less balanced, so again, you should definitely keep an eye on that. But again, this is considering strata as a continuous variable. The true test here would be to transform them into binary variables and see the balance within each dummy. So now we need to include this in actually an analysis. So how do we do this? So what we're going to do again is just run a linear regression. So we're going to do summary, the same thing as we always do. And we're going to do a linear model that is with robust standard errors. The outcome is going to be vote on 2002. And we're going to use contact. And again, I'm going to control by strata in this case. And my data, it's going to be my sample, but now my weights are going to be my weights for the average stream effect. And these two samples are the same, but I'm just going to use the augmented sample. Okay, right. So basically, I'm running the same thing that we ran before, the simple linear model, but now I'm using weights for an average streaming effect. So as you can see, we can just run that there, and we get an effect of 0.4, right? Which it's kind of similar of 4%, which is kind of similar to the 3.7% that we got with matching. Again, these are kind of similar. They're cousins. They're closely related to a certain extent. Okay, so we should expect to actually have similar effects. Okay, great. So now let's go finally back to our slides. One thing that you should notice though is that there are certain shortcomings of matching depending on how you use it. And I think that this is the part that I really want to highlight, okay? So many researchers actually misuse matching and confuse it with an identification strategy. So they think that basically just by using matching, they're buying themselves unconfoundedness, okay? Which is not necessarily true. Remember that we're under a very strong assumption here of selection of observables. We haven't still moved to the point where there could be unobservable characteristics that come into play for people to self-select into treatment and control groups, okay? So basically matching doesn't do anything for unobservables. We're only basically adjusting for characteristics that we can observe. So in terms of that, if the unconfoundedness assumption is not credible at the beginning of this, then matching doesn't do anything to solve that. So you should not confuse it with an identification strategy to that extent. So matching, again, it relies on selections on observables, which is a very strong assumption in that sense. And in order to make a valid causal claim, to a certain extent, you will need another source of exogenous variation. So in that sense, for instance, we will be talking next week about natural experiments, or for instance, difference in difference. We're going to be talking about regression discontinuities and a lot of things that you can have that will buy you sort of that exogenous variation and will make the ignorability assumption or the conditional ignorability assumption more plausible. In this case, however, selection on observables is usually something that will not hold. So just claiming that you can identify a causal effect because you use matching is not really a good idea. And it's all basically almost the same as claiming that you can identify a causal effect just by using regression with observational data, okay? You need something else in that sense, okay? So matching over regression, what it buys you is the non-dependence on the parametric approach, the fact that we're comparing like with likes. So it does have certain advantages in terms of an adjustment method over a typical regression. But again, it does not buy you anything in terms of an observables, okay? We're not dealing with that huge problem that it's what happened if people or units are selecting into treatment for things that I cannot observe. So even though I said that matching is not great for causal identification, which is true, it works actually great as an adjustment method, okay? And that is what I want to highlight in that sense. So for all the things that we talked about, matching what likes with likes, keeping the units of analysis intact, which is also a big deal. We're not relying on a sort of weighted average that we can't observe in that sense. We can look at our estimated counterfactual when we're using matching. We don't need to rely on parametric assumptions, and a lot of the times, depending on the matching strategy that we use, we can also run sensitivity analysis very easily to that extent, okay? And actually combined with other identification strategies like the ones that we're gonna see next week, natural experiments, diff and diff, things like that, it can improve results a lot, okay? And it can be a huge advantage over other adjustment methods. So basically the main takeaways that I hope you took from this class is that matching and weighting methods can be a great tool for your analysis, especially when you're using them, again, as an adjustment method. You can create more similar groups of comparison. You are actually making explicit the idea of the overlap region. So again, we're gonna talk a little bit more about this next week, also when we combine sort of both things. But the idea basically is that here you're not comparing two ends of a distribution that have nothing in common and no overlapping characteristics, but you're just focusing on those groups that have certain characteristics in common, okay? We are able to reduce model dependence, and also we can help with external validity under certain assumptions because we can make an experimental sample, for instance, resemble another type of population that we might be interested in. So next week, we're going to be looking at other identification strategies. So again, we're going to kind of move a little bit of this idea of selection and observables to a certain extent and try to rely on exogenous variations to identify our causal effects and hold our conditional independence assumption valid. And we're going to be looking at natural experiments and difference in differences. What assumptions do we need for them to hold? And how do I identify a natural experiment? Okay, a lot of things might look like a natural experiment, but maybe they're not. Assumptions come into play there as well. And the other thing is basically how we can combine also natural experiments with a difference in difference strategy. What does this buy us? Is this a good idea? Is it not a good idea? What are the threats to causality in all this? Okay. So that was the class today. I hope you enjoyed it. Please post your questions on Piazza. Reach out for office hours. I'm going to make office hours now available for a broader period. Okay. So if you're having any sort of questions, especially regarding homework 2, remember that there will not be answers during the weekend. So plan for that, especially because remember that the homework is due Monday, March 8th. And yeah, reach out, ask questions. It is okay to struggle with the R code. It is okay to struggle with the homework. We can solve a lot of the problems if you reach out in time, okay? So have a great rest of your week, and I'll see you next Monday.